I'm most privileged to have this great chance to sit with three outstanding human beings and scientists and have this rendezvous. Rendezvous in Chinese is 对谈. A little bit like dialogue. This could be a once in a lifetime chance opportunity, and I didn't plan for it. So in my 2 sentences, I mentioned about chance, opportunities, and plan. And that was the first slide that Dr. Oliver Smithies gave last Saturday morning. Have you been to the Saturday morning's seminar? Good. I think and you guys are so lucky because we are going to have a very good communication with 3 outstanding scientists. And they have share a very common features, like Dr. Britton Chance, Oliver Smith, and Dr. Smith's wife, Dr. Maeda. They are all smart, working very diligently. And I think they are very concentrated, particularly enthusiastic about science. And most importantly, they are still working every day, despite of Britton and Oliver's age. So before today's dialogue, I would make a short introduction of Dr. Britton Chance and Oliver Smithies and Dr. Maeda. And it is very difficult for me to do a very short introduction of them because they are giants and they have extremely wonderful records and bibliographies. But I try to make it short. And first of all, may I introduce Dr. Chance first? We Chinese respect older and also talented, whatever. So Britton Chance is the oldest people here. So let me introduce you first. He was born in 1913, and you can calculate what his age is. He's still working. He was the Eldridge Reeves Johnson University professor, Emeritus in University of Pennsylvania. And in his past, he has obtained 3 doctoral degrees. 1940 from UPenn in physical chemistry, 1942 in Cambridge, Oxford rival, in physiology, and 1952 in Cambridge in physics, perhaps, yes. And he's, he has published 4,000 papers and has been cited more than 10,000 times, or even more. And he's, when he was young, he discovered and invented so-called radar detector when during World War II, and it was used for the Second World War. And he has invented a lot of science technologies, and even now he's working on using near-infrared and LED to do the early screening of breast cancer. He's working on that. And he's now visiting this campus 1 month. This month he's in NCKU and working on this particular I think it's very important device. He has been receiving the honorary doctorate from this university in last February. And he's now our distinguished chair professor, visiting distinguished chair professor of IIS. And this is Britton. Yeah. And then I'll introduce Dr. Oliver Smithies. Of course, you all know him because he received last year's Nobel laureate in physiology medicine. And Dr. Smithies was born in 1925 in London. And he obtained his PhD from Oxford University. And then worked in University of Toronto, University of Medicine, University of Wisconsin Medicine. And since 1988, he was recruited to University of North Carolina, Chapel Hill, where our young scientist, Dr. Cai Yao-sen, received his PhD. And we know that he was awarded Nobel Prize due to his discovery of homologous recombination, which is very important and essential for the nowadays very state-of-art technology for transgene animals and knockout animals. But he has discovered many things. For example, gel electrophoresis. I remember in his talk, he was working on the technology, gel electrophoresis. On the January 1st, the New Year Day of 1954, he was working. And needless to say, he has received a lot of awards, and he has a lot of things to talk to you. Okay, so, and he has a very good better health. That is Dr. Maeda. And Dr. Maeda was his postdoc, and then become his wife. Of course, he may say something about this story. So I don't have to say too much. I'll leave time for them, and we can start from Britton first, and then Dr. Smithies, and then Dr. Maeda, and then they can ask questions to each other, and then finally we have 30 minutes. I'll control the time for our students and our faculty members to ask questions. Is it all right? Okay, so we'll start it from Britton.
Well, I'm very happy to be here, and I'm embarrassed to precede Oliver, who has so much to tell you as well as his good lady. But I've enjoyed my stay here at NCKU. I found the students to be stimulating, not challenging, but almost challenging. And the faculty to be committed to their jobs, and a wonderful coupling to the hospital, because my work involves the early detection of breast cancer by a non-invasive optical method, which I'm sure Oliver understands probably better than anybody else here. So the coupling to NCKU has been very positive, but I do think the students are what is important. And if by chance or some other way I stimulate them to work harder for their goal, then I will have done my job, because we are teachers and we love students, but we love students that perform better than others. So I have studied brain function with near-infrared light and found that indeed we can tell when the student has solved the problem, because like Archimedes, he will shout "Eureka!" and jump out of the bathtub if he happens to be in a bathtub, and run down the street without clothes. So I do think that you should be very conscious of how your brain is working, and whether or not you realize that there are new solutions to old problems, and that you can think about it and joyfully rejoice in a new solution. So that is my proposition to you. Know your mind, know how it works, and keep it working, as indeed Oliver has, and I've tried to.
Okay, before I turn this microphone to Oliver, I want to explain what eureka is. Do you know what eureka is? Well, they probably need me to explain. Eureka is that the word that 阿基米德有一天在洗澡的时候，从浴缸里突然跑出来，光着身子，这个跑到街上去，然后讲 Eureka， 他发现了这个阿基米德原理。Okay, so I try to explain in Chinese, sorry. Yeah, 所以 Eureka 就变成一个科学家的一个非常重要的 term， 叫做我发现了。Okay, thank you. Yeah,
Well, I have a marvelous opportunity to tell you a story as I was a student, because I remember reading Britton Chance's paper that he had written in 1949 maybe, so nearly 60 years ago when I was a student, and I remember even what the paper was about, and I haven't read it in between, but he was talking about this enzyme catalase, which is so fast that its speed of reaction is limited by the diffusion of molecules. And this was something quite extraordinary at the time, and I'm sure many people did not believe what Britton had found. Is that correct? Yeah. But you see, he was right. But I am remembering this because learning has always been for me something very enjoyable, and I hope I can encourage you that learning is not a difficult thing. It may be difficult, that's not quite the right word I want to say. Learning is not unenjoyable. It's not something that makes you miserable. It should make you happy to learn something new. And sometimes it takes a long time to learn something new. And I remember hearing a lecture or reading of the lecture of Richard Feynman, who is a theoretical physicist who got the Nobel Prize for many theoretical observations. And he said he loved to learn, but in learning a new subject, he would get a good book describing the new subject, and he would read the book, and he would get about a quarter of the way through and then could no longer follow. It was too difficult. But he would finish reading it, even though he didn't understand it yet. And then a little later he would pick up the book again, and he would start at the beginning, and now he found he could get halfway before he had to stop. He finished it again. And then the third time, he would get maybe 3/4 of the way, and by the time he read it 4 times, he could get to the end and understand all the way, which means that you have to work to understand, and but you should enjoy. And I'll add one little thing to that, because the Chaucer, the famous English poet, described the clerk of Oxenford. Now clerk in that case means a student. The student from my university, Oxford, had, in Chaucer's words, gladly would he teach and gladly learn, which means that as a student you learn and then you teach, and you have to enjoy both things. And if you do good research in the way, very good. But big thing is learn and teach.
Well, good morning, and I'm very glad to be sitting together in the middle of great scientists. I cannot come to that level yet. Hope I can sometime, but as some of you would like to think that way too. What I admire this great scientists is that their knowledge is very broad. They know electronics, they know physics, they know biochemistry, they know medicine. These days, including me, it's getting a little bit difficult to learn many different fields. You have to almost run toward one of your small goal, narrow goal, because competition is high and we are forced to somewhat. And that's probably unfortunate, that we should be more open-minded to many different fields. It could be literature, it could be art, it could be another field of science. I was trained as a chemist, organic chemist. I was lucky to be able to jump into medical field, like I talked about heart disease. But if some of you are working in physics, you can still study medicine, medically oriented problem, or vice versa, or chemistry. And these days, because we cannot do this, we try to make a group, and so get the physicists to help, chemists to help, and then biologists to help. And that's a very good way to approach a big problem. But also keep in mind that your training is chemistry, but when you get into some different field, that background helps you. It does not, you have to use your background. Often, if you see a problem, big problem, with different view, different ideas, with different training background, you get something different. New idea, you come up to a new idea, and that's very important. I just
perhaps learned a lesson from Oliver and Dr. Maeda, that you're always learning, that's what is exciting. In fact, in 1940, I was dumped into the radiation lab with Hans Bethe, Julian Swinger, and others who were physicists way above my head. And so it was a climbing expedition to get up to speed, to learn the approach of the physicists to new problems. They didn't happen to be biological, but they were technological. And so I was dumped into a medium that was full of novelty, full of learning, and you've got to learn. Fortunately, as I said, in our studies of high school students, we did get a signal of when your brain thought it had solved a problem, which was not always the same as the realization.
Talking about learning, I'll give you an example from myself, and that was in about 6 years ago, in 2002. I was attending a meeting in Sweden, which I talked about the work that I had been doing, and then another speaker talked about the work that he had been doing in relation to how the kidney works. And I listened to what he had to say, and it was very exciting. I didn't know anything about the kidney then, and so he opened a whole new area of thought. But in listening to him, I thought something was not correct in what he was saying, and so I asked him in the coffee break after his talk, and I don't need to give you the reasons for this. I asked him, why doesn't it clog? Because this was a problem in the kidney, and I thought it would block with the way he was thinking about it. And he gave the answer that all scientists tend to give when they do not know the answer. He said, oh, that's an important question, which means I don't know. But then I went back and got excited about this. And I had then 6 months or thereabouts to learn a completely new subject. Here I am at, I would be, how many, I have to work out how old, I would be 79, something like that. And I'm learning a new subject. But now it's a lot easier than it used to be, because I can go to the internet and I can get first of all, I can easily get titles, I can get abstracts, and I can do better than that. I can get the original article from the person. So instead of having to learn from a textbook, I can learn from the original literature. And that's very important, because a textbook is only a summary of what people believe now, and often not very good. And even reviews are very much biased. You don't see the data. You have to go back to the original paper and read the paper. No, don't just read the title. Don't believe the conclusions. The conclusions are what the writer hopes you will believe. But what is in there is you have to read the details. But it's much easier now than it used to be. That sounds strange, but it's easier to learn now than it was when I was a student. I had to go to the library maybe 3 times to get one journal because it would be out. And just imagine, oh, it's not there. Go back next day, oh, somebody's got it somewhere. And now you don't have to do that. So although there is more material to learn, it's easier if you work hard and systematically. So I would urge you to continue to learn. And that time for me, back in 2002, was like going back to school again. I had a marvelous time. I loved I loved the university when I was there. I enjoyed learning, and I had this whole experience again. So you can never stop learning.
Oliver, I forgot to tell you, I'm a kidney physiologist. but I can really understand what Oliver and Britton and Dr. Maeda said. We have to be very open-minded, and maybe I can add a little bit story from my own. Oh, okay, Britton, you want to go
not
first?
Not only to be open-minded, but to be doubting.
Well, actually, I was a kidney physiologist, and still be, okay. But I have to extend my research into tissue engineering, and a lot of time we went to people in biomedical engineering and also College of Engineering to ask for help, to ask questions. And I remember maybe 6-7 years ago, one time, we were interested in what's the rigidity or elasticity of a single cell. And we wonder how we can measure it. And so I went to an engineer, and he talked to me. This could be a good questions for nanotechnology. So from then on, we started to know what nanotechnology is. And we started to learn nanotechnology. And a few years later, with the help of those people in engineering and also physics department, we form a team and get funded from National Science Council with a huge grant on nanotechnology. And I was very happy because that huge amount of grant really support my lab to continue. So I consider that it's part of an open-mindedness. Don't just limit your learning in a narrow field. Try to reach out and learn more. Yeah. But I have a question here because I look at I went to Oliver's talk last Saturday. He discovered homologous recombination in year around 1985, right? You know, what age is it? What age he was? How old was he when he discovered the homologous recombination? 57, 58. And I was very impressed because I talked to myself. Yeah, I'm only 53. I still have opportunities. And students here sitting in the audience, you guys are at the age of 20s or even early 20s, right? You really have great opportunities. So I think that is my encouragement to all of the students here. And then I have a question to both of you. The question is very simple. What motivates you to work? Start from Britton. Okay.
Let me say what motivates me. I want to know the result. I want to see it. I can't stop. I cannot wait 2 days if I can see in 1 day. So that motivates me.
And I can add to that if we are working, and we work sometimes later in the day, maybe 7 o'clock, and Nobuyo may come and say, I'm about ready to go home. And I'll say, okay, well, just about 15 minutes more while I finish what I'm doing. And I finish half an hour later and go and look for Nobuyo. And she said, oh, just another 15 minutes while I finish what I'm doing. And this goes on and on. And sometimes we get home quite late. But it is this motivation of you can't wait to see what happens. That means it's very important to make sure that your work, you're doing something that you enjoy. Doesn't have to be something very important. It has to be something that you enjoy. If it becomes important, well, that's a bonus. But you may not get that. A lot of the time, I will do an experiment that makes a gel. Well, I love gel. So yeah, I make a gel and I get a pretty gel, and the result is awful. But I don't care. I have a pretty gel. So do something that you enjoy, and that helps with motivation. And make sure that you are, if what you're doing every day is something that you don't like, then go to your advisor and tell your advisor, I don't like running gels, if that happens to be. And your advisor should say, okay, well, we'll try to find something else that you can do where you don't have to run gels. And you can maybe you can go and look after the animals, and maybe you like, or whichever way around. So ask to change if you do not enjoy. And if your advisor won't help you, and I have said this before, but I'll say it again, then change your advisor.
Maybe I can say that the transition from war work to peace work, war work at MIT, radar laboratory, and peace work in Stockholm with Hugo Terrell on enzymes was a complete change of attitude, just as Oliver says. When the day ended when you were satisfied with what you did, not when the clock said 5 o'clock. And I think you must remember that training your mind is, as I said, the endless search. Carry on, don't give up.
I was, something popped out. I forgot to mention to you that Britain has won an Olympic gold medal in 1952, I think. 1950, let's see, what year is 1952? Summer Olympic on sailing. That's incredible, right? I forgot to mention that to you. Well, anyway, I try to summarize what they just talked about, and I think that's very important for our students. 研究的结果比成果还重要。大部分的学生都会想到成果，其实啊，他们迫不及待想知道的是这个实验的结果。如果这个结果呢能够变成成果，好的成果，那是一个 bonus 啊。但是我们不是常常在问成果，而是你 set up 你的 hypothesis， 做实验去证明，那个是一个结果，想知道那个结果，所以不要太过分去强调成果啊。可是你如果每次都有这个好的结果，有时候不好的结果也是很重要，所以同学们要在这里面这个多一点啊，就是说结果比成果还重要。他的意思是这样。I'm sorry 这个 ，but I think try to explain what you just said. Yeah.
Perhaps I can say, speak to the contrast between winning an Olympic contest and working in science. In science, there are endless opportunities to go ahead. In Olympics, when you cross the finish line, you know immediately how well you did. And so it's quite different where all your energies are concentrated on a single result of which you know about it. That's the finish line. While science, it is a wonderful continuum of effort and results. So I think that science is more fun. In the Olympics, perhaps it's a moment of glory. That wasn't the important thing. The important thing was that you were a little bit better than all the other contestants. And they were very generous in recognizing these small differences. So if I were you, I would stick to science.
Great.
Yes,
Oliver.
I would add something in a way to the Olympic story. That my hobby is flying airplanes, and when I was early in learning to fly airplanes, fairly early, my instructor, who was my friend, asked me if I would like to accompany him on a record, on an attempt to get a record to fly across the Atlantic from Labrador in northern Canada to Iceland in an airplane with only a single engine. And I might say I accepted the offer, and we did get the record. But something else you learn about when you learn to fly, and I have seen it when I have been teaching people to fly as well as when I was learning, and that is that you're frightened a bit. Everybody who learns to fly, or at least most people who learn to fly, are really frightened at the beginning. They think they're going to crash, or they're going to do something very wrong, and so sweat and you'll be frightened. You have to, and the teacher will teach the student to understand that it won't crash. If you do this, it won't crash even if you do nothing. And you slowly learn to overcome your fear of flying by the knowledge that you have learned. And I want to say that the same thing is true in science. That if you were taught, for example, if you have learned to do experiments with the kidney, and somebody comes along and you see an experiment in the heart. Oh, I would like to do some work in the heart, not in the kidney. I want to work in the heart. But I don't know anything about the heart, and I'm frightened I will not do very well. And so some people never then try. But I say you can overcome that fear of moving to something new by knowledge, by learning. Teach yourself. So you can overcome fear in science with knowledge just as you can in flying. Overcoming fear with knowledge.
Well, just a little bit different thing, but I just want to talk about what's the successful result. And you may be looking for the successful result. These days, we are forced to think about the project first, raise a hypothesis, and try to prove that it's correct. Now, this hypothesis-driven research makes us think that, okay, if we don't get the hypothesis correct, result is not proving it, it's the result is experiment is failed. But you have to think about it. What's the hypothesis? If a hypothesis, many of them probably are wrong. Now what your experiment, if it was done correctly, you prove that that particular hypothesis is wrong. You have to go back and set up another hypothesis. I find that particularly in the student, I had a lot of students, but students from Orient, because we respect our teachers, and that's very good, wonderful feature, I love that. But because of that, if I say something that, oh, I expect this to happen, then students tend to try to get the expectation to meet to the expected result. You have to, if this doesn't happen, you have to repeat because you might have made some mistake. But if that doesn't happen again, then you have to believe your result, not the expected hypothesis. So just then you have to learn to argue with your advisors.
Oliver just mentioned that he has a hobby of flying, fly a plane, yeah, airplane. So he just fly across the Atlantic. Wow, that's a very, very courageous trip, right? any kinds of creativity and innovations requires courage. So what they just mentioned is to encourage students to be, to have the courage to do good things, doing experiments, set up a good hypothesis, bold hypothesis, yeah. And Britton, do you want to add something?
To be sure, I admire Oliver's aeronautical skills. My brother also flew in his latter years, and a dear friend of mine, head of IBM, also flies a lot. And you have to be conscious of the weather. And in sailing also you have to be conscious of the weather, because a stormy day may sink your boat. So also you have to be able to cope with rapidly varying conditions, which are quite different from the experimental studies, where you can plan what you hope to do in a one day, and as Oliver says, you won't finish by 6 o'clock or 7 o'clock or 8 o'clock, because science is the never-ending trail. But if I were to choose between the two, I think I would choose science, because it is never-ending. It is always opening up new vistas, new insights, new data. And please remember that if you start on a problem, you may anticipate the results, but if you do, you're surely wrong. So it's much better to be expectatious of novelty, looking for the thing that you didn't expect, the thing that you surprises you. And this is the great boon of science, that it's a never-ending trail of unexpected events.
Yes, I think Oliver, you want to add? Oh, okay.
Well, I was trying to get her to say something that she had said to me in the past in talking about experiment. I think it is a quotation from Einstein that if you knew the results of your experiment every time, why would you ever do them? It's because you don't know the result that you do an experiment. And if the result is not what you expect, well, you have to think. But first repeat it, because you probably made a mistake. Many mistakes we make. And both of us have noticed the students at all levels who are doing a new experiment. And they will either read how to do the experiment from somebody else's paper, or they will use a kit, which is pretty bad, but possible. But then the experiment doesn't work. So what does the student do? Changes the experiment. That's a big mistake. They're much more likely that you have made the mistake, not the protocol or the other people. So if you try to repeat somebody else's work, don't change their method until you're sure that you have done it correctly. And that means repeating it, because it's easy to make a wrong addition, or to use the wrong pH or the wrong buffer or whatever it might be. So learn to repeat results before changing things.
I remember in Saturday's talk, Oliver mentioned that in perhaps 1986 or something, he was trying to amplify genes. And because PCR machine was not available on the market, so he ended up sort of making his own PCR machine. And he still used the machine. Can you tell us a little bit about that?
Well, it was quite interesting because once Kerry Mullis had described a PCR reaction, and he described that at a meeting in Cold Spring Harbor in the United States. The Cold Spring Harbor Symposia are very famous meetings where scientists talk about their work. And for example, Tonegawa, who discovered how genes are rearranged to make immunoglobulins, he first talked about it in Cold Spring Harbor, and I heard that talk. And when Kerry Mullis invented PCR, he first talked about it in Cold Spring Harbor, and I heard that and was very excited by this work. And slowly began to realize that I could use PCR for my work with homologous recombination or gene targeting. And so I contacted one of my postdocs who had gone to work, as it happened, he'd gone to work for Cetus, which was the company where Kerry Mullis worked and where the PCR was first done. And I asked my old postdoc to contact the people in Cetus and ask them if we could collaborate, and I would use PCR for my experiment, and we would have a collaboration. And they said, oh yes, we'll do that. But nothing happened. I waited 3 months, no enzyme, they were making the enzyme, no apparatus, nothing happening. So I happened to be in, I think Los Angeles, anyway, wherever, in California, and I went to visit them and talked to them some more, and they showed me various things. And because it was a scientific company, they made me sign something saying that I would, if I used any of their information, I would acknowledge them and give them the chance to make a patent, for example. And I did this, but when I came back, I thought, well, I didn't really learn anything that I had not already known, because I had heard Kerry Mullis talk. And so I wrote a little letter to them saying that this is what I learned when I was visiting your factory, and if this is, I think all of this material is already in the public domain. That means it's already known. And so I didn't learn anything new. But if you think this is not correct, please tell me. They didn't reply. So then, about 6 months later, I'm waiting for them to help. So Nobuyo knew in Wisconsin the person who had first isolated the enzyme, which many of you know, Taq polymerase, from Thermus aquaticus, the bacteria. And so we went and got the bacteria from the person in Wisconsin and began to make the enzyme ourselves. And I began to make the PCR machine. And I made the PCR machine. And then, because other people wanted the machine, I gave it to a local beginning manufacturer, and they began to make the machine. They never succeeded, but they began. Then I got a letter from Cetus saying that we are going to sue you because you are making a PCR machine, and you signed this document. And then I sent them back a copy of my letter to them and said, remember, I wrote to you and told you what I knew, and you never said there was anything new. So the patent the problem went away. But the message from this is, you don't make a machine to save money. This was making a machine to save time, because it was another 2 years before eventually the Cetus made a PCR machine, and when the enzyme became easy to obtain. So we saved a lot of time by making that machine.
Yes, Britton. Yeah, and also
Oliver makes a very strong statement that science and industry are separate. We have truth as our goal. They have money as their goal, and never the twain shall meet.
Sure about that, Britton. I think we have to learn to make them meet more often than we used to make them meet, because it can work together. But it's an interesting question in a lab that is developing new techniques and new methods, and something might be patentable. And then what are you going to do? Because maybe one person in the lab did the critical experiment, but the whole lab is involved. And so we eventually decided that if there was anything came from our lab that could be patented, then we would all share by putting the money back into the research if it made any money, not to any one person. But we never did get any patents anyway, so it didn't matter.
I just received a notice that students need to ask questions, and we have running out of time. But you know, we leave some time for students to ask 1 or 2 questions. Anyone in the audience? Yeah, please stand up and yes. Yeah.
Just like you just said, the aim thing says if you know the results of the experiment and why you're still trying to do the experiment again. I'm a freshman in NCKU this year, and I have taken my physics experience class, and I have many questions about that, because we already know the experience results and the numbers. Maybe it's not close to the truth, but we are still doing the same experience over years and years. And after I finished my experience, I found out my numbers is not that correct, and my teacher was said my experience is very wrong. I have to do it again. But I think I'm doing the experience. I don't care the number is correct or not. I'm doing hearing my experience. I learned a lot of new things, but why I should care about the number if it's correct or not?
Well, the answer is that you are learning. This is a part of learning, that you should be able to do an accurate and careful experiment. And if the experiment has been done many times by other people and gives a certain result, then you are showing to yourself, I can do careful experiments because I can get the same result that other people have got. So it is important to repeat experiments when you're learning. You have to be able to get a good result. That shows that you've learned to be careful. And so I would say I do not agree with you that you can have a poor answer. You should try to make your experiment good to get the correct answer. It's not important to do it over and over again. If you do it once and careful and you didn't do so well, well, maybe next experiment you'll do better. A different experiment, but you will do better than you did before. And each time you get a little bit better, and you can get closer and closer to the result that you expect in this case. Then, when you go and do your own experiment, you can believe your number. your number because I know that I can get good numbers. So I believe my new number is correct for your experiment, not the old experiment.
Yes, Cora, I think the last question.
Fine, but I still have a little question. What can influence, if there anything, your decision of which opportunity is promising in your scientific work? For example, like only personal interest, or like the supportive system, or maybe the contemporary trend in the research? I'm still wondering which could influence your decision.
Well, you have to choose, in making a decision as to what to do, you have to think at several different levels. The first thing is, what am I trying, in my work, what am I trying to do? Am I trying to help in curing a disease? Am I trying to help to understand how the kidney works? Am I trying to understand whether there is heart disease problem? So that is maybe your big aim, and you have this in your mind. That's what I would like to contribute. So now you have a choice here comes, and maybe there are three things, and perhaps one of them would not help in your big goal. So you can say, maybe I won't do that. Now you have two left, both of which might help to get you to your big end in the end. But one of them will lead to something anyway, will give you an interesting answer even if I don't get there. And the other one will not help anything if I don't get there. So then you pick the one that has two chances, here and here. And so now you've taken three and you've got down to one. So you choose, but then supposing you have more and you find that number three you don't like, don't do it. Do number two. You have to put all of those things in your head and work through them. And let the heart tell you.
Charles, do we still have time?
I think science is a big family, including biology and physics and chemistry and mathematics. And could you give us some suggestion to integrate this science to help us to think logically and to help us to solve problems? Because for me, it's really difficult. Thank you.
Well, I'll just give you one thought, and that is that if you don't have the basic knowledge, you will not be able to solve a complicated problem in whatever field you decide to work. So you should make sure that you get a good solid basis in chemistry and some physics and some mathematics, perhaps statistics. Get a good foundation. That's the first thing. And then you can choose more easily which way to go later on. But if you're missing something, if you find you're a biologist and you have not got enough chemistry to study your biology, go back and learn some chemistry. Or if you're a chemist and you're doing a biological problem and you don't understand how the kidney works, go and learn how the kidney works. So you can always go backwards and relearn or learn something new. But make sure that the basic knowledge that you have is good understanding.
I think we have, although science is endless, any party has an end. Any rendezvous has to stop. I would use the last minutes to say that I remember Britton has said this, science is people. And Oliver's mentor, Sandy Oxton, has already said something like very similarly, right? And today, my feeling is 如沐春风。你们有没有这种感觉？对啊，不希望它停止啊，希望再继续听下去，但没有办法，天下无不散的宴席啊。So I have to stop here, and let's give the biggest proud and thanks, Oliver, Britton, Nobuyo.